All right, let's keep looking at gases. So I'm going to make my box and I'm going to make my little gas particles in here. Gases have a lot of space between them. That makes them compressible. They have a lot of kinetic energy. An important thing about gases is the pressure that they're exerting on their container or against anything as they collide with it. So the four things that we need to describe what those gas particles are all about are the pressure, the volume, N stands for what? Moles, and temperature. So if we have those four things, we can totally describe what the situation is with regard to the gas. One of the things I think is so cool is that it doesn't matter what the gas particles are. They're mystery gas particles. They all kind of have these four things in common, working the same way, regardless of what the gas particles are. So in science, a lot of times we need to isolate what we call we need to isolate variables. So what I'm going to do is take two variables at a time and kind of show you how they interact. And a lot of this stuff you're like, oh, that makes sense. I've actually seen that happen. So we'll see what you think. So starting with the two variables, pressure and temperature. So the way this works is, as I usually start with temperature. As temperature, for instance, goes up, what do you think is going to happen to pressure? If temperature goes up, the little particles are moving faster and faster and faster, so the pressure would also go up. That's exactly what happens. And so that we say, since they have this, what we say, direct relationship, as one goes up, the other goes up. As one goes down, the other would go down. We say that they are directly proportional. And I don't know if you've run into this symbol before, but this actually is not an equal sign. Looks like an equal sign maybe, but also to me looks like an infinity sign. It's actually an infinity with a byte taken out of it. So it's the proportionality symbol. We say, we call it this. We say pressure is proportional to temperature. As one goes up, the other goes up. As one goes down, the other goes down. And in science, that's that's a trend, right? And that can be very helpful. We're going to quantitate that later. But see what you think. I've got a video to go along with that.
If the temperature of a constant volume of gas is increased, the molecules of the gas move faster, and each collision exerts a greater force on the walls of the container. In addition, because the molecules move faster, the number of collisions between gas molecules and the container walls increases, and therefore so does gas pressure.
Totally makes sense. I like things that make sense. Okay, so let's take another couple different variables. So we're going to deal with pressure again, and what's N? N is the number of moles. Okay, so to me this makes sense. I really kind of think of if you're blowing up a balloon, you're increasing the number of moles, and then what happens to pressure? Pressure goes up too. Now, not all, these are, again, we have what we call a direct relationship. Again, now not all variables are like this, but we see another trend. Okay, so we can say that pressure is directly proportional to N, the number of moles. Now, not all two variables are in sync like that. Some are opposite, and we're coming up to one coming up in a minute. So I've got, I think, another video.
If the number of gas molecules in a container is doubled, with no change in the temperature or volume, the number of collisions between gas molecules and the container walls doubles, which translates into a doubling of pressure.
You're like, I totally get that. Okay. Then the next one I want to look at is pressure again, but I want to switch it up to volume. Okay. So let's see. Now the example, and I think I don't want to give it away, but what if we were to have gas particles in this little box and the same number of gas particles in this big box? The same number of gas particles. I'm going to put, how about 6? 1, 2, 3, 4, 5, 6. So here we have, between these two anyway, the volume has what? Increased. Does that make sense? Okay, volume is increased. What has the pressure done? Well, the pressure is actually going to decrease over here because they have all of that room. So right now we have bumped up against our first relationship, that is what we say they have the inverse relationship of each other. As one goes up, the other goes down, and if volume went down, pressure would go up. So to show that, then we can use a proportionality symbol, but we then have to show 1 over x is the inverse of x. So we actually have to show it's proportional to the inverse. Okay. So anyway, volume and pressure are inversely related. We could say volume is directly proportional to the inverse of pressure. That's kind of how that goes. Bottom line is one goes up, the other goes down. As one goes down, the other goes up. So this is showing you that. So for instance, if you kind of look at the y-axis over here, as we decrease the volume, notice what's happening is the pressure is increasing. And here's a little video.
If the volume of a container of gas is reduced by half, but the amount of gas remains fixed, more collisions will occur between gas molecules and the container walls in a given time, leading to an increase in the force exerted on those walls.
And a good example is if you have a balloon and you squeeze the balloon to a smaller volume, what happens to the pressure? Well, you can feel the pressure increasing. So, very good. Well, we bumped up against an assignment slide. We've not done anything with numbers yet with gases, so see what you think.